everyone, welcome to our Unit C. So this is our physics unit. We're just starting. This is chapter 1 and it's on electric and magnetic fields. In today's lesson, we're going to focus on the 3 different types of fields and the field lines that are created by their fields. So by the end of this lesson, you should be able to define what a field is, and you should be able to compare the interactions between static electric charges and magnetic poles, and if you have 2 masses that are at distance. And these are what cause all these different pieces are what's going to cause these different fields that we're looking at. Right. So what are these fields that we're looking at? So fields are an invisible region around something that causes objects to experience a force. Okay. So what is a force? You've done force before. It's a push or pull. So it's an invisible area that's causing a push or pull on something, some kind of object. Okay. Fields can only be observed indirectly, so that means you can't actually see them. All you can see is their effects on other objects. So how do they affect other objects? So a field that you're very familiar with is our gravitational field. This surrounds Earth or any large object, and it's what's keeping us on Earth. So another field that we're going to be looking at is electric fields. And these have to do with electricity, electrons, and protons, positive ends, negative ends, that kind of thing. And then the third field is a magnetic field. So we're going to be talking about magnets and the fields that they create. All right, so we're going to start off with gravitational fields because it's probably the one that you're most familiar with. You experience this every day as you're walking on Earth. And it's an invisible region of influence where a force of attraction acts to pull a smaller object towards a larger, more massive object. All right. So all objects with mass will produce a gravitational field, but the objects have to be big enough to have observable effects. So you and I both create a gravitational field, but because the Earth is so much larger in mass, you can't see our gravitational field, or the Earth is much stronger. So same with the sun. So the sun creates a very, very strong gravitational field that Earth is always feeling, and that's pulling us towards the sun and keeping us in orbit, as is the moon. Moon is also affected by the sun, but because Earth is closer to the moon, there is a stronger effect on our moon towards Earth than the sun. So there is a relationship between the mass size for gravitational fields, but also distance. So closer objects are going to have stronger gravitational fields. Remember that gravity is an attractive force only, so it's not going to be ever pushing an object away or repelling something, only pulling an object towards the other object. Just to put into perspective the size difference, this image I like, you can see how much larger the sun is than the Earth, which you can just barely see there, and the moon you can barely see, but it's a little tiny blob there. So you can see why the sun has a much stronger gravitational field than Earth or the moon. All right, so our gravitational field lines, when we start talking about field lines, we want to see where this field strength is and how strong it is. So you can't actually see these lines, they're invisible, but we draw these lines to show where the field is, which direction objects will be moving, and where the stronger field is. So in this image here, can I move my image? Nope, can't move me. Okay, so you'll see the lower the concentration of field lines. So you can see here, there's when you have this when you're looking at this length here that they have, there's only one field line there. Whereas closer to Earth, in that same distance, you're going through about 3 field lines. So this is telling you that the gravitational field strength is much stronger and more concentrated closer to the surface of the object than it is farther away from the object. So you're going to feel gravity and that gravitational field much more strongly the closer you are to the object. All right. Oh, and I should just make sure we know always these field lines are going towards the object creating the field, right? Whatever the mass is creating that gravitational field. So those are our field lines. We're moving on to electric fields now. So electric fields are going to exist they're all around us actually all the time, because every charged object, whether it's positive or negative, can create an electric field on the force around it. So lightning, if you ever have static electricity, you've got a battery or a plug, all of these objects are creating electric fields. We may or may not feel them or notice them. So how do objects become charged? So remember that substances are all made of atoms, and in the atom you always have a positive nucleus and you have negative electrons that are orbiting that nucleus. So those charges don't disappear, but they can be transferred, okay? So they can't be created or destroyed, but they can be transferred. So when one object rubs against another, electrons are transferred. So protons can't really be transferred, but electrons can be transferred. So if you have two neutral substances, that means they have, so this would be like amber and this might be fur. They have equal numbers of protons and electrons between them, on each of them. And then when they're rubbed, sometimes the substance has a stronger preference or ability to grab more electrons, or just by chance these electrons are transferred. So the amber is going to pick up these two electrons, leaving the amber negatively charged and the fur positively charged. And then what happens when you have a negative and a positively charged object? They are going to attract each other, right? I should draw the arrows like that. All right, so remember that only electrons are actually going to get transferred. The protons have to stay in the nucleus in the atom. There's a great little video there where you can try this at home, where you can bend water. A little bit of magic for you. Probably have all the things you need to do. So make sure you watch that. And they do a great job of explaining why water is attracted to this object. Water is a polar molecule. That means it's charged. One side of it's negative, one's positive, and it can be quite influenced by other charged objects, like a PVC pipe in this case. All right, so I'm sure this has happened to you before. You've rubbed your hair with a balloon, and then you can stick the balloon to the wall, but then if you have long hair like me, that hair sticks up and tries to get back to that balloon. So when this has happened, all the negative electrons in your hair have gone into that balloon and made that balloon now negatively charged. And because all the negatives have left your hair becomes positively charged. Well, what happens between positive and negative? They attract one another. So that hair is trying to get to the balloon. So how does this happen? Well, conductors are really good at allowing electrons to move freely. And so if you can do this really easily with a conductor. Now you can do this with insulators as well. They don't transfer electrons, but they do allow electrons to move or be rearranged a bit more. So this is called charge displacement, when you allow electrons to move maybe from one end to another, or from one material to another. There's a little blurb in your textbook about lightning. I think it's on page 331. I would just read over that to see how lightning is produced. Basically, you have a buildup of charges in your cloud. The bottom of the cloud tends to have the negative charges on the bottom, and the top goes positive. They just kind of move around, but this causes the things on the earth to be, the positives come up to the surface where the negatives go down, to attract to the negatives that are up there. And once they get close enough, or you're able to have a pathway that lightning can follow, that's when you get the transfer of electrons and the lightning. But I would suggest reading page 313. There's a paragraph on there about lightning. Some other little lightning tidbits here. I love this picture of the Empire State Building with a big lightning rod, and that was actually its design. It was designed to be a big lightning rod for the city, and apparently it gets struck about 100 times each year with lightning, which is amazing when you think about it. At any given moment, there's about 2,000 thunderstorms happening around the world right now, and lightning strikes 100 times every second. That's just unfathomable. Would you really think about that? Right now, there's 2,000 thunderstorms happening somewhere in this world, and 100 lightning strike 100 times already. Like, I don't know how many times, because how many seconds have I been waiting on this? Anyways, interesting little factoids here. Your chances of being struck by lightning are only 1 in 600,000, but if you go live in Florida, it would go up. Apparently, Florida is the lightning capital of America. But lightning's not all bad. It actually puts the nitrogen in the format that plants need in the soil. So we need to have lightning to have plants. Some other little lightning facts. You'll see these lightning rods on the top of roofs of some buildings or houses. They are metal conductors, and they're connected to the ground. So they'll have a wire that connects them to the ground, so that the electricity will take this, or the electricity will take this easy path to the surface of the earth, instead of going through the house and destroying your electronics in the house. So they're always, lightning bolts, electrons are always looking for the easiest or the shortest path for them to go through. So when you're in a lightning storm, you always want to stay low so that you're not the easiest path for lightning and electrons to go through. You want to stay as far away as you can. All right, so how do positive and negative charges interact? Well, opposite charges, you probably know this already, opposites attract and like charges repel. So you have attraction between the negative charge and a positive charge, and you have repulsion between two of the same. Two positives and two negatives do not want to have anything to do with each other, right? So, and the more charged an object, the greater this force of repulsion or attraction becomes. So if this positive gets really big, like 5 times, then the force of attraction is going to get that much larger as well. So what about drawing the field lines for electric fields? The field lines are always going to be drawn from positive to negative. So positive to the negative, always. So remember that piece right there. And we can determine this by using what's called a test body. And in the case of electric fields, our test body is a positive charge. So basically what it means is, if you took this test body, a positive charge, and you put it into your electric field, which way would it move? How would it move? And that's how you're going to draw your field lines. So positives repel each other, so it's going to move away from the positive, but negatives attract. So that's where your field lines are going to look like this. Okay, so it's going to move away from the positive towards the negative. So you can see, how would a positive test charge work out here? It's just going to get away from that negative. Okay, so it's always, your lines are going to go from positive towards negative. Always, always. Your test body for an electric field is a positive charge. All right, so what is the charge of each of the red and blue objects? So by looking at these different electric fields, we should be able to say which side, the red or the blue, which is positive and which is negative. So knowing what we just said, we're always drawing our field lines from positive to negative. So we're negative. So positive to negative is how the field lines are being drawn. So we can always see where the arrows are pointing are going to be negative. So we see the arrows are always pointing here to this red side. So this red side must be negative, and the blue side must be positive. Right? So lines are always going from positive to negative charge. So in this case, it looks like we're going from positive in the middle to negative on the outside here. It's all negative around here. We'll take a look. The arrows are pointing to the red, so the red must be negative here as well. and blue must be positive. And again, the arrows are going away from the blue to the negative, and this must be a positive. All right. Now, your lines may not always go directly between the two objects. So in this case where we have two positive objects, our field lines are going to move away from the object, but not necessarily to the object over there. They're going to keep moving away from all the positives. There's nothing making them go towards them. So these will just be all away. There's nothing in between here. No field lines in between. In this case, you're positives to negative, so that one's a nice straightforward. You're going to see some field lines like this as well. Yeah. And then you might have some field lines just around the outside here too, coming in towards the negative and going away from our positive. And then underneath here we have two negatives, so I'm just going to draw them up here, two negatives. And we know that field lines go towards a negative, but they don't, but these charges are opposite, so they repel each other. So our field lines are going to look like this. Our positive charges are coming into the negative here and into here, but they're not going to attract each other at all. So there won't be any field lines in between them. All right, so that's drawing electric field lines. So you're out of the positive into the negative. So we're moving on to magnetic fields now. So magnetic fields, all magnets have two poles. They have a north and a south end. And this pair makes magnets dipolar. Okay. Polar means an end or a charge, and di means two ends, dipolar. So the attraction and repulsion occurs as similar with electric fields. So you probably played with magnets before. So what happens when you put north and north together? They don't like each other, right? They repel. Same idea. South and south, same idea. They do not like. Like does not like each other. Like does not like. What? Similar things don't like each other. Opposites, though, they attract. So north and south are attracting. Now, some elements have stronger magnetic properties than others. Like the group 8, 9, 10 on your periodic table make really strong magnets and are called ferromagnetic. These examples include iron, nickel, and cobalt. So what makes things magnetic and not? There are inside of everything, there are these tiny magnetic domains. Okay, these tiny, basically, think of them as mini magnets inside. And when they're all aligned in a compound or an element or in a substance, when they're all aligned, then you have a strong magnet or something that's magnetic. Okay, but you can have all these little magnetic domains all random and not lined up, and that would be a non-magnetic object. Okay, so like your towel that you dry yourself off with would not be magnetic, and all of the magnetic domains inside of that material are not lined up, so they're random. But we can make some objects domains, magnetic domains, line up by using an external magnetic field and putting an object in a magnetic field. We can turn things into magnets. Some materials, not all. There is some interesting little factoids on this page about magnetic fields. I suggest reading through it, and then there's a video on the next page. But it's kind of cool about how animals might use magnetic fields to, like, birds. We all know birds migrate, so they actually do rely on magnetic fields, and they've done some experiments where they've attached magnets on the backs of birds, and they sometimes fly in a circle, and they can't sense the Earth's magnetic field because they have this magnetic field on their back, which is quite interesting. This other one too, bacteria, the Australian mud bacteria, travel against magnetic fields during droughts to find water. Again, very interesting. Salmon, they may use that. Again, they have magnetoreceptors in their body that help them figure out direction using Earth's magnetic field. And same thing with foxes might even use it. There is a video on this next page here you might want to watch if you're interested on animal magnetism and how they use magnetic fields to get around. All right, so magnetic fields. So when we're drawing field lines for magnetic fields, you're going to use a test body that is a north. So basically, if you stuck a north in here, which way would it move? Okay, so if you stuck a north in, it's always going to move out of the north into the south. It's going to be attracted by the south end. So out of the north into the south. So north to south. That's the way you're going to see the field lines. And so you can see the field lines on this magnet, bar magnet, are going to be going around north to south. North to south. So there's a few more drawings here so you can see what happens if you have two magnet ends that are the same. So again, it's going to go north to south, so out of the north and away from the other magnet, out of the north and away. If there was a south on the other end, it would bend around and head to the south end. Another interesting little tidbit here is that, first off, the Earth's magnetic poles and geographic poles don't line up. So your geographic north is about here, but the magnetic north is slightly over here a bit more, right? So it's kind of off tilt a little bit. It's not like exactly the way we'd like to look at it on our maps. Also, the other interesting thing, if you ever thought about this, when you're using your compass and your compass is pointing north, at north end of your compass magnet is pointing north, it's pointing north because it's actually attracted to the south, right? North attracts south. So the north end of your compass, so let's say this is the compass, is attracted to the south end of the magnetic pole of Earth. So actually, our north geographic pole is technically the south magnet pole. Weird, hey? Woo! Anyway, just something to think about. There is some more about this in your textbook to really get a grasp on that. It's kind of an odd way to think. Alrighty, magnetic fields is another little anomaly that's created by our magnetic field. So our magnetic field actually on Earth helps protect from the solar winds. But when solar winds come in from the from the sun, they can get trapped or manipulate our magnetic fields. And where they do, they collide with the air and they can create some collisions with different gases, high energy collisions. And these different gases can get ignited or electrically charged. And they produce those colorful lights in the sky, the aurora borealis, or our northern lights, are caused by these two magnetic fields from the solar wind and the Earth's magnetic field colliding, and the different gases that are in there. Alrighty. Okay, so how do you get a magnetic field? So you may already have, if you have an object that's already magnetized, it's probably because it's magnetic because of the electrons that are moving around the nucleus. And this movement of electrons moving causes a magnetic field. You can also create a magnet using an electric current. So if you put electricity through coils of wire, you can actually create a magnet. And we're going to learn more about that in the third lesson, because this is how motors and generators are working. So we're going to look at that in a little bit. But it's good to know that electric currents actually can create a magnetic field. So as soon as you plug in something like a light or your computer, you also are creating a magnetic field. If you have a little mini compass and you want to do a little something, bring out a little compass and put it beside a wire, unplug the wire, and then plug the wire back in, and you'll see that compass needle change. Okay. All right, just a quick overview of the three different fields. So everything's all on one page here. So you've got the gravitational fields, and these are some examples: things falling to Earth, orbiting the sun, that kind of thing. Anything with mass is our test object. So if you put an apple in the gravitational field, will move towards the Earth. All right, and these field lines, these vectors, these arrows are called vectors because they're showing us the direction of the force, and they tell us the magnitude and the strength and direction of this force. Okay, so the more arrows there are, or the more intense the arrows are, the more intense that force in that field. Electric fields are created by anything that has a charge, and we use a positive test charge like this to figure out which way our electric field lines are going to be. Some examples of electric fields are static electricity and lightning. Magnetic fields are created by magnets, and they have two ends, north and south, and our test object is actually the north end of a magnet and which way it would move. So where would it be attracted to? So north moves to the south ends. Some examples: magnets, using magnetic fields, magnets using a compass. Also, the Earth has a magnetic field within it too. Alrighty, so there's some sketching here of some of the different fields. So think about these for a second, and then you can pause and try and draw them, and then see if you can get these right. These will help you with your assignment as well. I think these are very similar to the ones in the assignment, so if you've watched this video, you're going to get a little extra help on that assignment. So if you have a negatively charged balloon, and if you're looking at this, what kind of field is this? Is this gravitational, electric, or magnetic? If you said electric, you would be right. It's got a charged molecule, or charged particles are causing this field to be created. So if you have a negative charged object, which way are the field lines going to be? So if you're not sure, the test object for an electric field is a positive charge. Which way would the positive charge move? The positive charge is going to move to the negative. So the field lines on a negatively charged balloon are all going to be towards the negative. Okay. The next one, we have a magnetic, it tells us it's a magnetic field. It's a magnet, so a magnetic field. And how are our lines going to look? Well, our test is always what is a north magnet going to do, and that's how our field lines are going to be. So north is attracted to south, so that is how our field lines are going to go. So north to south. All right, and here we have an asteroid. Doesn't say it's charged, doesn't talk about being a magnet, so we're going to assume its gravitation is the main field strength here. Now there could be, like, obviously a balloon could even have gravitational field strength, but it's very minor, especially if it's a negatively charged balloon. So we're going to use the main gravitational field. The main field that's present when we're doing this. So we have an asteroid, and remember, gravitational field strength is always towards the mass. So it's always towards the mass causing the gravitational field. There you go. And that is the end of this lesson. Hope it made sense. If you have any problems or questions, make sure you get a hold of me.